All right, folks, today I want to show you how to work with parallel circuits, which are a little different arrangement of our resistors and our elements in the circuits. So a parallel circuit has our resistors, the elements of our circuit, connected so that one side of the resistor is connected and the other side of the resistor is connected. So if you go back and look at series circuits where they're connected end to end, that's a little bit different. You can see why they're called parallel circuits because it looks like these resistors are connected in parallel. And so if we look at what's going on here, I have in this particular example, a 24-volt voltage source. So, I've got my positive terminals this side of the battery, my negative terminals this side of the battery. If we think about what's going on here, everything that's connected to this node here is going to be the same voltage. Same thing down here, which, of course, that might be my ground. So if we think about the parallel circuit, the voltage from this point here to this point here has got to be the same as the voltage from this point here to this point here. So the voltage across the power source. And so when we think about a parallel circuit, one thing we find out is that the voltage is going to be the same for all elements in that parallel circuit. Just like with a series circuit, the current was the same. With the parallel circuit, the voltage is going to be the same. Now, as you might expect, things are going to be a little different for the current in a parallel circuit. So if we think about our friendly little neighborhood electrons moving around this circuit, they're getting pumped out by the battery. When the electrons get to this point in the circuit, there's now two paths for them to potentially travel. In my series circuit, there was only one way for them to go, which is why the current was always the same. So I'm taking this current, so my total current here, and I'm dividing the number of electrons that are going one way and the number of electrons that are going the other way. And so here I've got, for example, maybe I'll call that I2 since it's going across resistor number 2, and I'll call this I1 since it's going across resistor number 1. I've got two different ways the electrons can travel. Now, of course, just like with the series circuit, the total voltage was the sum of all the individual voltages. This total current going through the circuit is going to be the sum of the currents going through these different paths that electrons can travel in the circuit. This is just what's called conservation of energy. All my electrons got to be accounted for. I can't magically have more electrons going this way. Every electron's either got to go one way or the other. So I'm going to show you guys how to use kind of an ugly looking little equation here. This is probably the type of equation you're going to see in your physics class. And I don't super like it because it's not a very intuitive equation. But if you remember, our idea, if we got lots of resistors, is to try and replace my complicated resistors by an equivalent resistance, a single resistor that's equal to the resistances of my original circuit. And so this is the equivalent circuit. I got 24-volt power source, and I can replace these two parallel resistors by a single resistor. And the equation for that parallel resistance is given by this complicated equation. I'd take fractions of my resistors, add them together, and then I'd flip that fraction, and that gives me the equivalent resistance. It's not too terrible. You got calculators, you punch this into a calculator, easy enough. And so if I'm plugging in numbers here, if I want to find my equivalent resistance, I got 1 over R1, which is 12, plus 1 over R2, which is 24, and I'm raising that to the negative first, so I'm taking the inverse of that. So 1 over 12 is really what? 2 over 24. 2 over 24 plus 1 over 24 is 3 over 24. And 24 divided by 3 is 8, so 3 divided by 24 is just going to be 1/8. And if you think about this little power to the negative 1, all that is the inverse of the fraction, so that means flip the fraction, easy peasy. That tells me that that tells me that the equivalent resistance that I could replace these two parallel resistors by is a single resistor that is 8 ohms. And once you have this guy here, Ohm's law is a piece of cake to figure things out. So of course, like we said, I got my total current going through here. Woo. Sorry guys, I still don't have my drawing tablet, so I'm trying to do this with the mouse. But this right here is just a simple application of Ohm's law. So everybody knows V equals I times R. Here my voltage is 24 volts. I is the thing we're looking for. In particular, we're looking for this total voltage. Times my equivalent resistance, which is just 8 ohms. Divide both sides by 8, and I get my total current has got to be 3 amps. And so that is this total current. Now, here we know now our equivalent resistance. We know our total current. We know V1 and V2, they're going to be the same as my voltage source because they're all connected to the same positive and negative terminals. All that's left to do is figure out what I1 and I2 are, which again is just another application of Ohm's law. So if we look at resistor 1, well, I got my Ohm's law. So V equals IR. The voltage across R1 we know is 24 volts. I in this case is what we're looking for. In this case it's I1. And R we know is 12. So R1 in this case. And that's easy enough. Divide both sides of that equation by 12 and I get I1 is equal to 2 amps. And let me do the same thing for the second resistor. So V equals I times R, Ohm's law. Here I'm looking at resistor number 2. So the voltage, it's the same as all the other voltages. So that's 24 volts. We're looking for I2. And to do that, we're going to use the resistance for R2, which is 24 ohms. Again, easy peasy. 24 divided by 24 is 1. So I2 is just equal to 1 amp. And of course, if you look at I1 and I2, 2 plus 1, that adds up to what we figured out I total was, 3 amps. So easy way to double check your work. So this is using my equivalent parallel resistors formula. If you have more than one resistor, you just keep adding your resistances. So it'd be like 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 and so forth. Add those together and then do the inverse of that fraction, flip the fraction, that'll give you your equivalent resistance. I'm going to show you guys an easier way to think about this in the next video, so stay tuned for when that's posted.